Yeah. Shut it off there also. It's possible.
Do you know how to turn that off?
Yeah. Yeah.
Okay, I'm not sure I will use a blackboard. So I think you will see enough computer screens and so on for the day that, I will just give a talk like this. So I'm a mathematician, and what I want to explain is, if you want, the sort of a very strange relation between computers and mathematics, and the role of Mathematica in what I have been doing. So, for a long time, I have been a sort of ferocious advocate of the fact that one should compute by hand, and that the long, very long computations, I will give you an example, are exactly the time when a mathematician can, the mind, if you want, is sufficiently free that the concepts can emerge. And the example, which I will give, is the following. I have a collaborator, Henri Moscovici, and with him, at some point, we were working on some problem, and at some point, that was in 1995 or something like that, at some point we realized that in order to compute the result that we absolutely wanted to get, we had to compute an expression which was really, really complicated, and which was about, if you want, 1,000 times one page of computation. And so we decided to do it independently, competing, of course. And I'm not lying, we computed for 3 weeks, 8 hours a day. So, I mean, this gives you an idea of the size of the computation that's going to do. Now, after doing this computation, we communicated. Of course, we found that each of us had made some small mistakes and so on. We corrected these mistakes. Then we tried to find out whether the result had the expected property. It didn't have the expected property because we had made a strategic mistake. I mean, a mistake, a real one. Then we understood why, of course, because we had been very slow in doing the computation and so on. So we understood. And eventually, about 1 year later, a concept emerged. And this concept is the concept of cyclic homology for Rolf algebras, which is a very involved concept. And at that time, I was a very strong advocate of the fact that this concept would never have emerged if we had used the computer. And the reason that I was putting forward was the following, was that it was only because we were so familiar with every term in the computation that the concept emerged in a free way. I mean, we were, after that, our mind was sufficiently used to all the details of the computation, all the little wheels of the computation, that the structure emerged. And it emerged completely naturally, without any effort. And that was the same when, years before, I was computing with cyclic homology, and eventually there was a small category which emerged with classifying space, P infinity of C, and it emerged as being the structure of the computations. Okay? So the problem which I had at that point with the computers was the following, was that I knew that there were some young people who, when they wanted to multiply by 10, were using a computing machine to multiply by 10. So what I was completely aware of the fact that if you want, you give up, and if you don't feed your mind with computation in real time, being done by hand, then you run a very serious risk, which is the risk of if you want, delegating to somebody else and not being really conscious of the content of the computation. So that was my situation in 95, 96. Okay. Then what happened is that a few years later, I was working on a problem with another collaborator, Michel Dubois-Violet, and at some point, there was again an expression that we had to compute. It was again a crucial expression because it was a Jacobian of non-commutative geometry of some map. and we needed to know whether this Jacobian was zero or non-zero according to the values of the parameter. Okay. Now, this Jacobian was given as a sum of certain integrals over a period of some functions. But that sum had 1,440 terms, and each of the integral was an integral of rational fraction in theta functions and their derivatives, which was of degree 16. Maybe you had like 16 theta functions which are occurring there. Okay? So at that point, we knew that even trying to compute one of them, the only thing we could do, it was depending on certain parameters. So the only thing we could do was to compute the Q expansion. There was no way to get a closed form. So we had to compute the Q expansion of this expression. And of course, the Q expansion had coefficients which were trigonometric expressions. Okay. So at this point, the only thing I could do, of course, is to use the computer. So I used the computer, and I had a laptop, of course. I had Mathematica on the computer. And the only thing I could do is compute what is called the trigonometric expression. So the trigonometric limit, if you want, is a limit when you don't take into account Q, you take a limit, okay? And that is, of course, computable with Mathematica. And so I put it on my laptop, okay? I put the laptop to work, and it took the laptop a full night, okay, to give me the expression. And the expression was beautiful, because, if you make the sum of 1,440 terms, you don't expect it to I mean, if you have a conceptual reason, of course, okay, then you might expect a miracle that it's a nice thing. But there it was factorized, okay? So you could get the zeros for that limit in a very simple way. That was okay, but of course it didn't give us any clue about the full expression. Okay. So then I had the luck to communicate with Michael Trott of Mathematica. And we discussed, and we were exactly in that type of problem that we had to shrink the length of the computation. The length of the computation, if you put the Mathematica expression in with integrals and so on, it's out. I mean, you cannot do it. It's far too long. But the integrals were of a special form and so on, so we could simplify the program to compute the integrals and so on. We had a long exchange and so on. And then we could compute up to the term like Q squared. But this was not enough. It was not enough because it was depending on parameters. There were two parameters, eta and m, and there was parameter q. So, with two terms, you cannot go very far. You cannot, okay. So then, with Michel Dubas-Violette, we came back, we thought mathematically and so on, and we found a simplification, mathematical simplification, that was shrinking the time by a factor of 60. Okay, and that was, of course, already big. So then we could compute the term in q to the third power. But it was not enough. Okay, with the term in third power, we could begin to see some elliptic functions which were appearing as a function of the parameter eta and m, but we had no clue for the dependence in Q. Okay, so eventually I found a way to connect myself to the big computer in École Polytechnique. Okay, and I could use time on this big computer. And then what happened is that it became apparent, to compute with computing the next power, it became apparent that we were right with the guess we had for the elliptic functions, which were occurring before, but there was a new phenomenon, which was that there was an overall factor which was only depending on Q. Okay? And this overall factor looked very, very strange. So we thought a lot with Michel about the various terms that we had got in this thing, and we recognized the ninth power of the eta function of Dedekind. I mean, the first terms in the development. Okay. So then we made a prediction. It's like a prediction in physics. We said, okay, it should be like this. Okay. And then eventually, by making more and more simplifications, both in the mathematics and also in a computer program with Michael Trott, okay, and again using the computer in Polytechnique, we were able to compute several next terms, and we checked the conjecture. Then we input this conjecture in the paper, in our paper that we were working on, okay, and eventually we found some mistake in some encyclopedia. We had been using some formulas. These formulas were wrong. Okay, we checked that by Q expansion and so on, and eventually we found out that this result simplified tremendously. Okay, and it was giving an algebraic result, and with this algebraic result, we could eliminate the use of theta functions in that problem. So here I think it's completely obvious that by human computing, you cannot do that. It's impossible. So I mean, what would have happened otherwise that we would have given up, okay, we would have stopped, and we would have said, perhaps one day we can find, but I mean, the route to find this concept, eventually we found the concept because we found the reparameterization and everything in rational terms and so on, which was unbelievable from the start. So there, if you want, it's completely obvious that the computer played a major role. But what I must say, however, is that the reason why I was using Mathematica at that time was that it's something which a priori is very useful for engineers and so on. So for mathematicians, it's extremely good because it's user-friendly. And people would believe that mathematicians would know the C language and so on. No, I mean, we are mathematicians, we do something else. And what we need is something which is user-friendly. Okay, and there I found, if you want, an enormous advantage. But I would be honest, I would not have gone very far if I had not known Michael Trott, who was able to communicate with me and to give me some access to some sort of more difficult part of the computation. Then what happened is that, of course, then I was convinced by the power of the computer. But then it turned out that the concept that we had discovered with my friend Moscovici in our work, and this of algebra and the of cyclic cohomology, turned out to be related to modular forms. And it turned out that there again we had formulas, but these formulas were of a level which was far more abstract than the level that I had met when I was computing with Michel Duboviolet with theta functions and so on. So the level of abstraction was like this. There was a Hopf algebra, and one had to prove some associativity, one had to do a tensor product of the Hopf algebra over a subalgebra. Okay. And again, discussing with Michael Trott and so on, we were able to put up a program which was able to do that. I don't have the slides, but I mean, if you would see the slides, you would see that it's formulas for certain expression in the tensor product of algebras, and it's ranking Cohen bracket. So you have an RC2, RC3, RC4, RC5. RC2 is very, very simple. It's a very simple expression. So you can check associativity by hand. And you can give it as an exercise. Okay. RC3 is already taking half a page of formulas. Okay. So if you want to check associativity, you can do it, but it will require a lot of manipulation, a lot of work. Okay. So in fact, we wanted to be sure that there was no mistake, and so we wanted to check associativity for RC5. So then, this time I didn't contact Michael Trott because I really wanted to be able to do it myself. But what I had to do, I had to go inside, I had to tell the computer that instead of iterating, 250 times, like it does usually, I had to lift the iteration level to more than 10,000. And then the computer worked. It worked, and eventually it proved the associativity for RC5. And that was really incredibly impressive, if you want, because it was something at the level, I remember in the academy once, there was a report in the academy about the role of mathematics in society and so on. And some people had written that the computer will only be able to check some numerical cases. So, when I saw that, I jumped because I knew already, of course, how to use the computer to make actual checks and actual proofs, which are complete proofs, of course, and which are not dealing, of course, with numerical evaluations. I mean, this has absolutely nothing to do with numerical evaluations. I mean, it's a computation. It's a computation which is very elaborate, but the computer does it. And another example, very recent example, is that, as I said, I have always loved to do these very long calculations by hand. The reason being that I believe, it's kind of éloge de la durée, if you want. I believe that when you do these calculations, the mind is in a certain state, which is very special, because after a while you do the same thing, more or less, and the mind is free, but it knows what it's talking about. It's a kind of meditation state, if you want. It's a kind, in meditation you learn you have to count 1, 2, 3, 4, and so on, and do it repeatedly like that, and have your mind to be free. When you compute by hand, okay, you reach such a state of meditation, okay. And what had happened is that I had another collaborator in 1989. We made a calculation with Paula Cohen. We made a very, very elaborate calculation. And at some point we found a result, okay. But we did by hand. And again, it was something which was taking a full notebook. I mean, by a notebook there, I mean, a real book like this, and which was full of calculations and so on. Okay, and we didn't publish it because we were sort of unhappy about the result. And last year I met her, and we decided that maybe we should put out our calculation. But you know how the brain functions, and at some point in my brain I said, okay, but this calculation is very strange, because we were getting a very complicated expression in terms of the modular operator, of the Laplacian, and so on. And I said, this calculation doesn't fit with another result which I had found with another collaborator, and which it was not a proof, it was a kind of formal argument, but this formal argument should have implied that this result should have been much simpler than what it was. Okay? And, but the trouble was the following. The trouble is that at that time when we did this calculation, there were so many reasons to be unsure about the result, if you want, because there were so many steps done by hand that the probabilities that we would have made a mistake along the way was so great that we didn't try to simplify the result at the end. Okay? So what I decided to do recently is to reduce this calculation with a computer. Okay? So of course I redid the calculation with the computer, redid it, fine, and the computer found on the nose the same results that we had found. So we didn't make a mistake. Okay? But then I said, okay, now I should try to show that the result is indeed as complicated as it looks. Okay? So I tried some examples. This time it was numerical examples. And I always found something very simple. Okay, so then I said, okay, there must be a reason, there must be a reason why okay. And eventually, of course, by using a little bit the computer and also using hand calculation, okay, I found that the result was simpler than it looked, and that in fact it implied the analog of the Gauss-Bonnet theorem for what is called the non-commutative terms. And the epilogue of the story is very amusing, because then we wrote a paper. I would have showed you the one page of the paper where we put a formula, because the formula was taking 3/4 of a page, dense, 3/4 of a page, dense formula. Okay. On the other hand, we had done this proof only for a very specific conformal structure on the non-commutative torus, which was the rectangular one. It's like, if you want, the elliptic curve that you get is very special. I mean, it's a very special value of the tau parameter in the elliptic theory. So in the paper we said, okay, we believe the general result is true, but we only did the calculation in this case. Fine. Of course, we were hoping that some other people would take over and do this calculation. And, okay, of course, very soon afterwards, some other people working in the same domain said, okay, we'll try, to do this calculation in the general case. And I was in correspondence with them for about 6 months, and I was getting worried, because the reason why I was getting worried was that it was absolutely crucial that the result would be the same. Otherwise, that kind of formal proof I had done would fail. Okay. And very recently, and they put the paper on the archive just Monday of this week, okay, they succeeded to finally do the calculation, to do it to the end. But now, and this is what I would have shown you in the file, but it would have just distracted you. Now, the formula which in the paper with Paula Cohen was half a page, now it occupies 7 pages. And of course, you cannot do it by hand. I mean, the point is the following. The point is that if this is something you would try to do by hand, forget it. Okay. So, I mean, it's quite interesting. The only thing which I regret not to have shown you is one page by Galois, which I had on the slide, and in which, very interestingly, you can find it in the complete works of Galois. Galois was already reflecting on this problem of the complexity of the calculations and if you want, of how to deal with it. And what he was telling, of course, is that we all know that there is something which is called elegance in geometry and so on. And of course, the best situation is a situation in which you can guess a short formula and find an abstract proof of the short formula. But Galois was not advocating this at all. He was saying that if we would do that, we would be very soon stuck because of Euler, and if you want, it is necessary to do these long calculations. But what he was saying was extremely interesting. What he was saying is that it is extremely important to not really do them completely, but to imagine the result, and then after imagining the result, using this result. And what happened recently is another use which I made, again with my friend Michel Dubois-Dolec, and which was the following. Namely, there was some variety which was defined by 10 equations in 25 variables, okay? And we wanted to understand, okay? And using the computer, we found that it was a rational variety, so it was parameterized rational. But the rational parameterization is something which you can do with Mathematica, but if you ask Mathematica to give you the rational parameterization, Mathematica will spend perhaps 1 minute just showing it. Namely, it will not occupy, 1 page. It will occupy several pages. So what to do when you have something like that? Of course, what to do, is something very simple. You don't... I don't know if there is a chalk. You do this. Okay, but the computer has it in its memory. Okay, and then what you can do is do what Galois was saying. Now it is in the computer. Okay, and now you can use it. How do you use it? Because Michel was saying, okay, well, this curve which is associated to the solution will always be trivial. Okay, fine. I told him, no, come on. So I took random number. I took random number as the data in this thing, okay? And then I computed the curve, and of course the curve was an elliptic curve, so it was not at all a trivial curve. So what I am saying is that there is this way of using the machine, which is very close to what Galois had in mind, okay? And which is amazingly powerful if, on top of that, one has the possibility to take a generic point, namely to use a random number, and so on and so forth. And the final example which I wanted to show you, but it's not necessary to show the graph, is the following, is that there is another use which is much easier, of course, of Mathematica, because it's not calcul formel, if you want. But there is another use which is, in fact, quite convincing, and which is the following, which is that now Mathematica has the zeros of the Riemann zeta function in the machine, okay? And in our work with Katia Consani, we were working with an expression which was supposed to be a counting function, and which was supposed to give you a kind of a function that would be positive, but would have an extremely strange behavior. It was a distribution. It had to be positive for values of q which are bigger than 1. Okay? But the value at q equals 1 had to be minus infinity. So this is a very, very strange behavior, which you would never expect. Okay? Now, with a computer, you can... And the expression that was given was the sum over the zeros of the Riemann zeta function. So it's something which, for working with ordinary mathematician, it might be you can compute 3 zeros with some digits and so on, but you will never get anything close to the function that you want with 3 zeros. You need something like 1,000 first zeros and so on. The expression was an expression like this. It was the sum of q to the power rho plus 1 over rho plus 1, where the rho varies among the non-trivial zeros of zeta. Okay, there was another term, but this was the main term. So now what is really amazing and extremely convincing is that if you take the sum, of course not over all zeros, but like from 10,000 first zeros, okay, and you ask Mathematica to plot the graph of this function, then it turns out to plot exactly what you expect. And and this is quite amazing, because if you want it, it shows you that you didn't make any mistake. So this is another use of Mathematica, in the sense that I consider it as, if you want, it's a little bit like if you were a physicist and you would work about very abstract theory and you would never have any contact with real experiments and so on. So here it's the same. There are many domains in which the formulas look so, how to say, abstract and complicated and so on, that nobody can really test them concretely, okay, like testing for a sign mistake and so on and so forth. But now it's perfectly possible. So the only thing that I would say is that there is still, and I had a long discussion with Michael Trott at the time about this. You see, when you write with Mathematica, when you write simplify, I tried before I came, but I have the program number 7, so okay. But if you write simplify Jacobi Sn square plus Jacobi Cn square. Well, I should have put of x. Okay. Okay. Then Mathematica gives you Jacobi Sn square plus Jacobi Cn square. Okay. So there, if you want, what I would say is that I think it's extremely important for the development of Mathematica that people realize that after all it's Mathematica. So it has many applications for engineers and so on. But I think it's quite important that there is one side of the development which is pure mathematics, and which tries to implement in special functions as many as possible simplification rules which are not yet present. I mean, the same thing for hypergeometric functions. I mean, there are simple identities for hypergeometric functions which are not implemented. And I think it should be a very important part of the research project of Mathematica that, if you want, these things are implemented in the simplified method. I mean, the simplified method works wonderfully well when you work with trigonometric functions. I have to tell you one thing, just to, so that you understand the complexity of the calculation I was doing with Michel Dubois-Viollet. Okay? When we were doing this Q expansion, we had this sum of 1,440 integrals. Okay? You have to know that when we were computing to Q to the power 9, each of the integral, the Q expansion, was 250 pages of trigonometric expressions. Each of them. Okay? So of course, the simplify method was crucial, because you had to simplify at the right time. If you had added, these expressions, it would have been totally impossible. So I think there is a part of the development which was not mentioned, but I think it's very, very important, and which is that it can be a formidable tool for pure mathematics. I mean, I use it all the time because but there are two things which have to be thought very carefully about. The first one is improving the simplify, really improving the simplify for special functions, for lots of things, okay? And the second thing is that we have to find a way not to jeopardize this amazing possibility that, if you want, a mathematician can ask that when he does calculations and at the same time his mind can think, because it puts in this kind of mode. So one has to think. I have more or less succeeded, to get to that stage. For instance, now I am computing with Witt polynomials and so on, and for that the computer is, you cannot avoid using the computer. But what I mean is that I think it's quite important to think, because to try to avoid this terrible fact that young people, when they have to multiply by 10, they use a machine. So you see what I mean? I mean, there is a kind of interface, a kind of boundary, very delicate to situate between the end computation. And end computation, I don't mean end computation that you compute with a piece of paper and so on. It can be also end computation with Mathematica. I mean, it could be, you could use the format of Mathematica to do it. But I mean, there are computations where, if you want, you think at each term and so on, and the time where you really use the power of the machine. I mean, I think there is a real question, and this question is extremely important, because if you want, you know very well that if you
ask the computer to do too early a calculation, it will be a mess. What you will get, is something which is useless. So you have to think. You have to spend a lot of time thinking and even trying to do the calculation yourself, taking work and so on, before you resort to the computer. But the issue that I am talking about is exactly how to, to situate this and how to improve this interface between the calculation done oneself, and the thinking and the use of the computer. Okay, so I think I will stop.